So I'm going to begin talking about the structure and property of carboxylic acid derivatives. In the previous chapter, we looked at carboxylic acids. These are the five main derivatives. Another one is the carboxylate salt, the conjugate base of carboxylic acids. These are referred to as derivatives because when they're split or hydrolyzed, they form carboxylic acids. And in some cases, they are made from carboxylic acids. Not all of them, but some of them are. Okay, so all the derivatives can be converted to carboxylic acids, to the carboxylic acid by acidic or basic hydrolysis. Esters and amides are commonly found in nature. Acid halides are actually too reactive to occur readily in nature. There's not very many examples of anhydrides in nature, but there are a few. But again, they are pretty reactive. Right, this is an example of a reaction that we did in lab. This was a banana oil, the isoamyl acetate. We took a carboxylic acid, which was acetic acid. We took isopentyl alcohol, 3-methyl-1-butanol, and with a little bit of sulfuric acid catalyst, we refluxed and we obtained the ester and water as a byproduct. This is an equilibrium, so when we did this in the lab, we had to use an excess of acetic acid. Sometimes an excess of alcohol is used. In our case, we used an excess of acetic acid. All right, let's start with esters and their nomenclature. Okay, with this one, this is derived from formic acid or methanoic acid. And so this is 1-methyl-ethyl methanoate, or could also be called isopropyl methanoate, or isopropyl formate in the common nomenclature. Okay, if we replace the isopropyl group with an H, this would be formic acid. Right, this is phenyl benzoate. Okay, this part of it is the benzoate. Benzene ring as a substituent is a phenyl group. Okay, this is derived from 2-phenyl-ethanoic acid or phenylacetic acid. So this is methyl 2-phenylethanate or methyl phenylacetate. Okay, so the first word is derived from the alkyl group of the alcohol, or phenyl in the case of a phenol. The second word is from the carboxylate group of the carboxylic acid. Cyclic esters are called lactones. And again, there's a common and an IUPAC way of naming these. This one is called delta valerolactone. Valeric acid is pentanoic acid. And the delta comes from, okay, if we start, this is the carboxylate, this is the alpha, beta, gamma, delta. So that's where the ring closes. In the IUPAC, this is 5-hydroxypentanoic acid lactone. Okay, if we were to split this, we would get 5-hydroxypentanoic acid. And to form the lactone, we would split out water and form the ring. Okay, so this is alpha-methyl gamma valerolactone in the common nomenclature. In the IUPAC, it's 4-hydroxy 2-methyl pentanoic acid lactone. Okay, if we were to split it here, this would give us 2-methyl or 4-hydroxy 2-methyl pentanoic acid. Okay, let's look at amides next. This is formamide or methenamide, derived from formic or methanoic acid. We replace the OH with an NH2. Resonance stabilization is very significant for amides. This is why amides are not basic, because you can see in one of the resonance structures, the nitrogen carries a plus charge. Amides can be thought of as a product of the reaction of a carboxylic acid with ammonia or an amine. Okay, they're not basic because the lone pair on the nitrogen is delocalized by resonance. The CN bond actually has a lot of double bond character. Okay, so when we protonate amides, since the nitrogen is not basic, it's actually the oxygen that picks up the proton. Okay, just like with amines, we have primary, secondary, and tertiary amines. Primary, secondary, and tertiary amides. These are classified by the number of carbons directly bonded to the nitrogen. Okay, looking at nomenclature of amides. Okay, again, we locate the longest carbon chain that would contain the carboxylate group. Okay, so if we replace this with an OH, this would be 2-phenyl propanoic acid. And so this becomes 2-methyl propanamide. And if we have a substituent on the nitrogen, these are located with a capital N. So this is N-ethyl, N-methyl, okay, that should say N2-dimethyl propanamide. Okay, so that's not correct. In the common nomenclature, this is N-ethyl, N-methyl isobutyramide. Okay, so this would be derived from isobutyric acid. Okay, earlier we said that cyclic esters are called lactones. Well, cyclic amides are called lactams. And here we have 4-aminobutanoic acid, also called gamma-aminobutyric acid. This is a neurotransmitter. And if we eliminate water from this NH2 and this OH, we can form a cyclic amide or a lactam. And so this is 4-aminobutanoic acid lactam, or gamma-butyrolactam in the common nomenclature. Right, this is what's called a beta-lactam. It's 3-aminopropanoic acid lactam. Okay, so if we were to open this up, we would have 1, 2, 3, we would have propanoic acid, and we would have an amino group on carbon number 3. This is 6-amino hexanoic acid lactam. And here we have 4-amino 2-methyl pentanoic acid lactam. Okay, so if we split it here, make this a carboxylic acid, we've got 1, 2, 3, 4, 5. Okay, so that's where we get the pentanoic acid. And then there's a methyl on 2. Okay, before we go on to nitriles, let's go back to the opening slide. Okay, up here at the top, this is a penicillin antibiotic. And one of the notable features of penicillin antibiotics is they have this beta-lactam ring. The bacterial proteins have a NH2 group, which attacks the carbonyl, and because of ring strain, it opens up this ring. And when the penicillin or cephalosporin also has this beta-lactam group, that binds to an amino group of the bacterial protein, and then this serves to inhibit synthesis of the cell wall. Okay, it's become somewhat of an arms race because bacteria have developed resistance to penicillin, and one of the ways to deal with penicillin resistance is to include an enzyme which breaks down the beta-lactamase enzyme or inhibits the beta-lactamase enzyme in the bacterium. Okay, so back to nitriles. Nitriles are considered a derivative because if we hydrolyze, let's go back. If we hydrolyze or split a nitrile, we get a carboxylic acid. Nitriles can be hydrolyzed under basic or acidic conditions. If they're hydrolyzed under basic conditions, you get the conjugate base or carboxylate of a carboxylic acid. Okay, the nitrogen ends up as ammonia. Acetonitrile or ethane nitrile has a similar structure to propyne. Okay, it contains a triple bond, 1 sigma and 2 pi bonds. It's a linear molecule. The non-bonding electrons on the nitrogen are not basic for a nitrile. In common nomenclature, this is called acetonitrile. In the IUPAC, it's called ethane nitrile. We don't drop the E. Okay, in this middle example, the carboxylic acid takes priority. So the CN group is a cyano. So this is 3-cyanopentanoic acid. The nitrile group cannot be part of a ring, so it's incorrect to call this cyclopropane nitrile. Instead, it's cyclopropane carbonitrile. Okay, propane 3 carbons, and then there's actually 4 in this compound, and then the carbo takes care of the 4th. All right, let's look at acyl halides next. It's more accurate to call these acyl rather than acid because we can have acid chlorides of phosphoric acid, for example, or sulfuric acid. Acyl specifically refers to chlorides of carboxylic acids. Acid chlorides or acyl chlorides are by far the most common. You can also have acyl bromides. These are considerably more reactive than carboxylic acids, and so they are commonly used to synthesize other acid derivatives such as esters and amides. Acid chlorides, as I mentioned earlier, don't ordinarily occur in nature because they're so reactive. We've seen acyl chlorides used in the Friedel-Crafts acylation to make acyl benzenes or phenylketones. Okay, so this is derived from propanoic acid. And so we drop the IC in the acids, becomes propanoyl chloride. This would be 3-bromobutanoyl bromide. Okay, next we'll turn to anhydrides. These are often confused with esters and ketones, but they're neither. They're actually more reactive than both of those. They're called anhydrides. And anhydride means without water. And so if we combine two molecules of a carboxylic acid with loss of water, we form an anhydride. Anhydrides are more reactive than acids, but less reactive than acid chlorides. When we do an acyl substitution, which is what's shown in this diagram, nucleophile attacks, we go through this tetrahedral intermediate, oxygen pushes down, and then it kicks out the carboxylate group, which is a fairly good leaving group. Okay, this occurs in two steps rather than one because the incoming nucleophile and the outgoing leaving group are not collinear. Instead, they're actually perpendicular. So that's why we need to form this tetrahedral intermediate. Okay, so this is ethanoic anhydride. Let's go back. Ethanoic or acetic anhydride. This is an important material for the synthesis of aspirin. Okay, here we have trifluoroethanoic or trifluoroacetic anhydride. Okay, if we were to break this, if we were to hydrolyze this, we would get 2 molecules of trifluoroacetic acid. We can also have mixed anhydrides. Okay, so this is ethanoic methanoic anhydride. Okay, here's the methanoic, here's the ethanoic. This is also called acetic formic anhydride. This is also a useful synthetic material because it's very useful for making formamides and formate esters. The formic acid group is actually much more reactive than the acetic acid group. Okay, nitrile has priority over alcohol. Okay, so we have 1, 2, 3, 4. We've got butane. We count the nitrile carbon. So this is carbon number 1. We have a hydroxy on carbon number 2. So this is 2-hydroxybutane nitrile. Okay, notice that we retain the E in butane. Okay, this is a summary of the priorities. Acids are way up at the top. Then we have esters, amides, nitriles, aldehydes, ketones, alcohols, amines, alkenes, and alkynes. All right, let's look at boiling points of carboxylic acid derivatives. And then just for comparison, normal alkanes are included. Okay, so acid chlorides are the most volatile. Okay, and then alcohols are also included here for comparison. Alcohols are similar to nitriles of similar molecular weight. Carboxylic acids are higher boiling. And then primary, secondary, and tertiary amides, you notice they have the highest boiling points. Esters are actually pretty methyl esters are actually pretty volatile too. Fairly similar to alkanes and acid chlorides. Okay, so why are amides so high boiling? Okay, because of intermolecular forces. Okay, we have dipolar resonance. There's actually a lot of large charge separation. We can have strong hydrogen bonding in the case of primary and secondary. Let's go back here. Okay, notice the primary amides are the highest boiling. And then you also have intermolecular attractions because of this charge separation. Dimethyl formamide, okay, which does not hydrogen bond with itself, is a liquid at room temperature, and it has a melting point of -61. Okay, this is a useful solvent. It dissolves a lot of organic compounds. It's also miscible in water. N-methyl acetamide, which is a secondary amide, you can see that the boiling point has raised. And then the primary amide, propionamide or propanamide, melts at 79 degrees. So these all have the same molecular weights, but different boiling points. Dimethyl formamide has the lowest because of lack of hydrogen bonding. Tertiary amides cannot hydrogen bond, but still have high boiling points. Okay, what about solubility? Acid chlorides and anhydrides are too reactive to be used with water or alcohol, so it's meaningless to talk about solubility of acid chlorides and anhydrides in water or alcohols because they react. Esters, tertiary amides, and nitriles are good polar aprotic solvents. Some of the solvents that are commonly used in organic reactions: ethyl acetate, dimethyl formamide, acetonitrile, dimethyl acetamide is also used. Okay, you can see that DMF or dimethyl formamide has a high boiling point, as does dimethyl acetamide. Okay, these amides you can see are all miscible in water. These small amides. Acetonitrile is miscible in water. Ethyl acetate is 10% soluble in water. Ethyl acetate is sometimes used in solvent extraction in a separatory funnel as the organic phase. Okay, let's look at infrared spectroscopy of carboxylic acid derivatives. Ketones are included just for comparison. You notice they have a similar carbonyl stretch. Both of these will have a lower frequency if the if the carbonyl is conjugated with a benzene ring or a double bond. We can easily distinguish a ketone from a carboxylic acid because the carboxylic acid will have this very broad OH stretch. In fact, it'll be on top of the CH stretch. Esters will usually be a little bit higher, 1740, 1750 for the carbonyl stretch, a little bit higher than acids or ketones. Okay, amides will be significantly lower for the carbonyl stretch. And this is because of resonance, the CO bond has a lot of single bond character. If we have NH bonds, then we'll also see additional peaks, 2 peaks for an NH2, 1 peak for an NHR. And of course, no peaks between 32 and 3500 for a tertiary amide. Acid chlorides will have a higher carbonyl frequency, usually about 1800. Anhydrides will show 2 carbonyl peaks at about 1800 and 1750. The nitrile stretch occurs just above 2200 wave numbers. All right. Okay, so here we have ethyl octanoate, which is an ester. The carboxylic acid portion has 8 carbons. The carbonyl stretch shows up at 1739. That's the most significant. We do have a couple of CO single bond stretches. This is often unreliable because this region of the spectrum is usually complicated. The only other feature of this would be the saturated CH stretch. Okay, looking at lactones and lactams, notice here that ring strain increases the carbonyl stretching frequency. We also see that with lactams. Okay, so here is propionic or propanoic anhydride. Notice we have 2 carbonyl stretches. Okay, what about proton NMR absorptions? Okay, for comparison here, okay, alpha hydrogens will show up at about 2 to 2.5, whereas ether hydrogens will show up at about 4. Amide N-hydrogens will show up at about 3. Okay, those on a carbon directly attached to the nitrogen. The NH absorption is highly variable, often between about 5 and 8, and often broad. Okay, and then we have some similar compounds. We have an aldehyde, a formate, a formamide. The aldehyde shows up about 9 or 10, whereas these others show up at about 8. The hydrogens alpha to the nitrile show up at about 2.5. Okay, so here is dimethylformamide. Okay, the formamide hydrogen shows up at about 8. And notice the methyl groups are distinct. They're different. Okay, because there is a lot of double bond character in the CN bond, free rotation is restricted, and so we have 2 methyl peaks because this one is trans and this one is cis. Okay, and the carbon-13 NMR for an ester, the carbonyl carbon shows up at about 170. The ether oxygen shows up at about 60 to 90. For an amide, the carbonyl is also about 170. And for a nitrile, the carbon shows up at about 120.